The gradient is a vector that we build from all of the partial derivatives of a function. It points in the direction where the function increases the fastest. In words, the gradient of f is the vector whose first entry is the partial derivative of f with respect to x, and whose second entry is the partial derivative of f with respect to y. In symbols, gradient of f equals, open bracket, curly df by curly dx, comma, curly df by curly dy, close bracket. A directional derivative tells us the rate of change of a function as we move in one chosen direction. In words, we find it by multiplying the gradient by a unit vector pointing in that chosen direction and adding the results together. In symbols, directional derivative of f in the direction of a unit vector u equals gradient of f dot u. Here is the same idea shown two ways. On the left, we see a flat, two-dimensional contour map of the surface, with the gradient drawn as an arrow pointing uphill. On the right, the same surface is shown in 3 dimensions, and that same arrow points straight up the steepest slope, so you can see both views describe the same climb. Now let us work through a full example. Let f of x, y equal x squared times y plus y cubed. We want the gradient and the directional derivative at the point where x equals 1 and y equals 2. First we find the partial derivative of f with respect to x. Treating y as a constant, curly df by curly dx equals 2xy. Next we find the partial derivative of f with respect to y. Treating x as a constant, curly df by curly dy equals x squared plus 3y squared. Now we plug in x equals 1 and y equals 2. The first component becomes 2 times 1 times 2, which equals 4. The second component becomes 1 squared plus 3 times 2 squared, which equals 1 plus 12, which equals 13. So the gradient at this point is the vector 4, 13. Suppose we want the rate of change in the direction of the vector 3, 4. Before we can use it, we must turn this vector into a unit vector, meaning a vector of length 1. The magnitude of the vector 3, 4 is the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16, which is the square root of 25, which equals 5. So the unit vector is 3/5, 4/5. Now we take the dot product of the gradient with this unit vector. Directional derivative equals 4 times 3/5 plus 13 times 4/5. That equals 12/5 plus 52/5, which equals 64/5. 64/5 simplifies to 12.8, so the rate of change of f at the point 1, 2 in the direction of 3, 4 is 12.8. For our check step, we compare this to the largest possible directional derivative, which always equals the magnitude of the gradient itself. The magnitude of the gradient, 4, 13, is the square root of 4 squared plus 13 squared, which is the square root of 16 plus 169, which is the square root of 185, which is approximately equal to 13.6. Since 12.8 is less than 13.6, this confirms our answer makes sense because we moved in the direction 3, 4, rather than exactly along the gradient direction, and only moving exactly along the gradient would have given us the maximum value of 13.6.